Hi, everyone. It's a pleasure to see you at our meetup, Tech Internals Community Meetup. By the way, everyone who joined us, please let me know if this is the first meetup that you joined by Tech Internals Community, or this is not the first one. Anyway, for the ones who are joining our meetup just for the first time, I would like to start it with the short presentation about Tech Internals Community before passing it to our speakers that will give a talk on different and very interesting topics. So really short about Tech Internals Community. We are the leading conference for developers of complex and highly loaded systems. Basically, our aim is to build a community from developers for developers where they can exchange their knowledge, their skills, and also think on the solution for difficult problems that everyone faces on their everyday job. Basically, we are hosting the number of free meetups. Maybe you have visited another ones, but the main event of ours is going to be here in Berlin on 26th of May. So you can scan the QR code that is at the moment on the screen to join us. But of course, I will tell a little bit more about the conference further. A little bit about us in numbers. So we have already organized over 100 events for developers of highly loaded systems and decided to bring our product to Berlin because it's a huge IT hub and we would really love to build a community here. This is the key topics of our conference. So it's architecture, DevOps, software engineering, monitoring, tracing, QA, performance testing. And what I would like to mention is that we are extremely tech conference, so you will not find talks about time management, marketing, or whatever. This is purely tech talks. So this is some examples of the top talks from the previous conferences. In terms of the audience, there is lots of information in here, but I would like to draw your attention to the right-hand side, where you can see that most of the attendees of Tech Internals are senior people. So middle plus specialists are joining our conferences, again, because of the level of the talks. And our amazing speakers also represent our community, so you can evaluate the value of the talks today, like a demo version of them. This is the reasons why people attend Tech Internals conference. So first of all, it's of course, as I've mentioned already, top speakers and cutting edge topics. Then of course, building the community of like-minded professional, Q&A zones, networking, and of course, entertainment and after parties. So you can network, drink beer with like your mates and your colleagues, have fun, but also exchange your knowledge. So basically, I will show this. I will show this QR code a little bit later one more time, but in here you can scan it already and use this promo code to buy a ticket for the conference with a 10% discount. So this discount is specifically for the ones who joined us today. It's TIC promo 10. So please scan it. I will give you a minute, but of course, at the end, after the talks of our speakers, I will give you another chance to write down the promo code and also to follow the link to our website. So just give you, I don't know, maybe 1 minute. And also, of course, again, let me know if you are here for the first time. Let me know in the comments section if you are here for the first time, or maybe you have already seen our meetups, have visited them. At the end, I will also tell you a little bit about our upcoming events, because we do have series of meetups, which I would like to highlight. So please follow us to keep updated, to stay tuned. So I think, again, I will give another opportunity to scan the QR and to write down the promo code. Also, we will share it with you in the afterwards emails. And now I would like to pass it to our first speaker, Edoardo, please. Let's begin your amazing talk. We are really curious about it. Thank you.
Thank you. So, hi, everyone. Okay, so my name is Edoardo Vacchi. I'm going to tell you about Wasm. I'm not sure you can see my screen already. Oh, there you go. All right. So the title of the talk is putting the Wasm in Wasm from Bytecode to native. We're gonna do a deep dive into how WebAssembly runtimes work. I'll start with a couple of words about me. I'll be short. I'll keep it short. I worked recently. I've been working on WebAssembly runtimes. Last couple of years, I worked for a company called Tetrate on a WebAssembly runtime for Go called Wazero, and most of this talk is going to be about Wazero. But I've recently joined a new company called Dylibso, where I still contribute to Wazero, and to a new WebAssembly runtime called Chicory, and I'm going to spend a few words about Chicory as well. So Wazero is a Go runtime written for WebAssembly. And Wazero implements both an interpreter that is portable and runs pretty much everywhere Go is supported, but also Wazero is a just-in-time, is an ahead-of-time load time compiler, optimizing compiler for WebAssembly. And it supports MD64 and ARM64. Now, Go is a compiled language and doesn't really do just-in-time compilation. So the way Wazero works is kind of peculiar. I'm going to spend a few words about those specific details, but what you're going to see here, it's something that is true for any WebAssembly runtime. I'm also going to spend a few words, if we have enough time, about Chicory, because it's a new project, but it's made leaps and bounds. It was recently, like yesterday and even this morning, on the front page of Hacker News, which is pretty cool. Wazero's been there a few years ago, a couple of years ago, but it's been there quite frequently, but Chicory is the first time it's there, so it's pretty amazing. So it both implements an interpreter for WebAssembly that runs on Java, and again, this is portable everywhere, but it also compiles, translates WebAssembly into Java bytecode for better performance, and we're going to spend a few words if we have enough time for that. All right, so, and it runs on Android too. So before we deep dive into that, I wanted to give you a quick introduction to Wasm, because I don't know if the audience is aware, but I mean, it's been a few years now, so I suppose most of the people have heard about WebAssembly at least once. But a lot of people might think it's just a technology for the front end, because it was born there. It was born out of the necessity to have an alternative to JavaScript or a complement to JavaScript to write high-performance code. WebAssembly was created to provide a better compilation target, because people were targeting JavaScript as a compilation target. It is designed to be safe, to be portable, and it's a bytecode representation. The main goal, the first goal, first and foremost, was to be high performance, to allow to write high performance application on the web. But that does not mean necessarily the browser, even though it was born for the browser, because it does not make specific assumptions for the web, specific features, does not provide specific features for the web. In fact, it can be embedded in other platforms. Of course, in the browser is where you might have encountered already without even noticing. Google Earth uses WebAssembly. Most games that run in the browser will use some extent, WebAssembly. Figma, the popular graphic design application, uses WebAssembly. Shopify uses WebAssembly. Google Sheets uses WebAssembly. So what about outside the browser, which is the part that I'm actually most interested in? So the thing that is most interesting to me and to us as a company is software extensions. So when it comes to software extension, you've written, let's say, a large C++ application, large native application. You want to provide some way for your end users to write some extensions to script this application. And usually there are two choices in the mainstream today, usually. I would say Lua or JavaScript. But then you are making a choice for your end users. You are choosing for them the language they will have to use. By choosing WebAssembly, you choose a VM for a language that is much smaller than a JavaScript VM, for instance. It's kind of minimal, it's kind of quick to start, and it's definitely easy to embed. So some companies have already made this choice. For instance, Red Panda, it's an alternative Kafka implementation written in C++, and they use WebAssembly to provide to their end users a way to write data transforms using any language that they might want. And we'll see that there's a few languages that are supported. Envoy is an HTTP proxy that provides scriptability to their end users. You can define filters in a number of ways. There are built-in filters, there are native filters, but there are also WebAssembly filters. And Envoy was among the first applications that embraced WebAssembly as a way to provide scriptability to end users. So Wasm lets your users write software extensions using their favorite language because it's a compilation target, and so any language that is able to compile to Wasm can be supported, and to run it in a sandbox environment. I just wanted to spend one word about Xdism. It's not a product, it's an open source project that it's a layer that lies on top of multiple WebAssembly runtimes, and Dylibso developed this open source framework. Essentially, the way you can interface with WebAssembly might require some, some work. And so you might need to understand the low levels of WebAssembly. And in this deep dive, we're going to see those details. But if you don't need or don't want to learn all of that, Xdism provides a framework on top of that to define plugins using a higher level interface. And it abstracts away from all of the possible runtimes you can run, so that you can embed WebAssembly in any language that you want to use. So we provide Wazero for Go, we provide Chicory for Java, and we use, I don't know, V8 for TypeScript, and that. I also wanted to spend one word about mcp.run. It's something that we built on top of Xdism and on top of XTP, which is another thing that we did. And you can find it online. You can write your agents. You can write tools for your agent using WebAssembly, using all of these tools that I mentioned. And it's pretty fun to work with. So if you want to try it, please do. All right. Oh, you can write a Telegram bot with just a few lines of prompting and using the tools that are available there. So it's pretty cool. There's a tutorial online. But let's talk about Wasm now. So how does Wasm look like? So if you write Wasm in Go, it looks like just a regular Go function. And again, it gets translated to something like this. This is how the bytecode looks like, at least in its textual representation. It's a stack machine, so you get the parameter using this local get opcode, and then you put it on the stack, and then you get the second parameter, put it on the stack, then the subtraction operation pops two values from the stack and pushes the result. It's a stack machine. Now, how do you interface with it? So if you use a browser, you can fetch and load a WebAssembly module, and then invoke a function among the exported function from that Wasm module. So in this module, we are exporting the sub function. We'll call it sub, which obviously is the one we define here. And then we can call subtract from there. And you can do the same using Wazero. The API is slightly different, but it does pretty much the same thing. It subtracts two values and gives you 8, obviously, the same results, even if it's two different hosts. So the way the program where you embed your WebAssembly runtime is usually called the host, and the WebAssembly module is called the guest. So Wasm is barebone. So as I mentioned, you can embed it wherever you want. One of the things that it's peculiar to Wasm is that it comes with no standard library. It's pure compute. It only does operations, computations. So if you want a comparison with something you might be more familiar with, if you're familiar with the JVM, with Java Virtual Machine, the Java Virtual Machine and the JDK are all of this diagram here. So the JDK is all the libraries, even its layer, even the language. The JRE is the layer that goes just below that layer of framework. And the hotspot VM is just the bottom of all this diagram. And Wasm is as if it were exactly this layer here, just the VM, just the compute, just the thing that interprets or evaluates bytecode. So how does Wasm interact with the Word? Well, you have to provide functions that you can import from a module. For instance, if you want to read a file, it will have some sort of signature like this. And then from another module, from another from another function, you can use the function that you have imported. So the Wasm module by itself, it is not capable of interacting with the operating system. It cannot open files. It cannot write files. It cannot open network sockets. It cannot even look at the time, really, without interfacing with the operating system. And these are provided as capabilities through imports. And this is the way this WASI system interface works. WASI provides a set of predefined functions that you can import, and you can think of it as a sort of a POSIX layer for Wasm, except it's sandboxed because you provide access to these capabilities by a way of explicitly giving it access. All right, so I already mentioned this. Modules import and export functions, and that's the way you interact with them. So if you want to read a file, let's say you want to load a config file, and this is wrong. Obviously, this is meant to say read file. So if you want to load a file, you will import a function to read that file, and then you can provide some parsing to this load config file. But the read capability itself will be provided by this external function. And then how would you provide these external functions? Well, you provide them by providing them by configuring your WebAssembly runtime. In JavaScript, this is the way you would do it. In Go, this is the way you would do it. But it's pretty much the same thing. You would provide the implementation of a function, and then the WebAssembly runtime calls that function. It's really calling an external function that is defined using the host language. And this is why they're called the host functions. So many programming languages are able to target Wasm. There are compiled languages, there are interpreted languages. So Python, Ruby are often interpreted, or even JavaScript. But it depends if there's a compiler for that specific language. Other languages that are more generally compiled. So Rust is compiled, Go and TinyGo are compiled, Zig, Kotlin, and more. So TinyGo was the first languages in the Go family that the first compiler that gained capability of targeting Wasm, and I would argue the first choice because it designed to target small architectures, and because of that it generates small binaries. So that's usually what you want to do, especially if you want to create plugins. But recently Go has even in 1.24 especially, it has gained full capability to compile Wasm binaries that work as you would expect. And so today you can even use Go at the cost of having larger binaries. So Wazero, as I mentioned, is pretty portable. In fact, you can even compile, now you can use the Go compiler to compile Wazero into Wasm. So you can run a Wasm inside Wasm, so you can, Wasm while you Wasm. So how does Wasm really work, though? So there are many runtimes, there are different strategies to execute Wasm. All of these are native libraries. So if you want to use Wasm using these, you will have to link, and you want to use Go, you will have to link against a native library. The most famous probably is V8. This is also a JavaScript compiler. This slide is a bit outdated because the name of the engines are now different. They're different engines, but that's how it used to work, and it still works this way pretty much. It's a tiered compilation engine. Essentially, it doesn't just load the Wasm module, but it compiles it first using, it doesn't just compile the module, it first compiles it using a fast compiler that used to be called Liftoff, and then it compiles them if their cost of compiling is worth it, using a more efficient compiler that generates better code. However, because it generates better code by doing more passes, and thus it takes more time to compile. So the strategy for a tiered compiler is that first it compiles using a quick compiler that generates slow code, but better than the interpreter, and then it uses a faster compiler, a slower compiler to generate faster code. Wazero is kind of different, but it works pretty much the same conceptually. It was born in 2020 because Takeshi wanted to scratch a particular itch. All of the compilers, all of the WebAssembly runtimes at the time were native libraries, and when you link a native library against the Go runtime, you have to go through an FFI. And an FFI means generally when you have a runtime that it won't play very nicely with that runtime. That is true for Python, for Java, or for Go. So what kind of issues you can expect when you link against a native library? Well, portability issues, because now your tool chain will have to deal with a native binary that might not be available for all the platforms that you want to support. You might have tooling issues because now the native binary is opaque to your tool chain, to your tools for those specific language Go in this case. Runtime issues because the native binary does not really know about your Go routines, about your garbage collector, about your virtual threads, so it won't cooperate with them. So Wazero avoids all of these issues entirely because it's essentially a very special Go library. So you can still have all of the features that make Go, static linking, cross-compilation, Go routines, but it will work in concert with them. Go will work nicely with them. So how does that work, really? So I already mentioned this. We both have an interpreter, but that's not a default mode of work if you are on any supported platform, and that means pretty much everywhere. MD64 and R64 are the targets for our load time compiler. The way this works is that using the Go API that I have shown earlier, you load at runtime, you load a Wasm binary, and then this binary is compiled in memory. We can also dump the result to a cache on disk, so you don't have to compile it over and over again. And at a runtime, you can instantiate your module as many times you want, and you won't pay the cost of compiling it. So finally, we got to the point of the talk. How does function compilation works in Wazero? But this is how, in general, it works on most WebAssembly runtimes, really. So first of all, you decode the module, and then you go through a compile routine. If you go in the interpreter engine, if you go into the interpreter flow, you will follow one specific flow. If you go through the compiler, you will follow a different flow. We will focus focus to the compiler now. So as I mentioned, this is a multi-stage, multi-pass compiler. We support ARM and MD64. Our compiler draws from several compiler architectures, V8, LLMs, and even Go's own compiler. First we decode, then we actually compile. And the way to compile is that we have a front end where we translate into an internal representation called the SSA. It's a textbook internal representation, and then we go through an optimizing phase that is architecture independent. And then the backend is the place where we translate this internal representation into proper machine code for that specific architecture. We do instruction selection, we do register allocation, and then we encode the binary into a byte slice, and then we execute that. So how does that work? All right, first, let's say we have a function that does a sum and then a subtraction, just to have a few more instructions here. And then we translate, so we load this, we parse it, and then we translate, we validate it, and then we translate it into our SSA, which is a tree-valued set of instructions, which is pretty much standard. Here are the value that are the result of these expressions. And then we have some jumps. We have a way to represent the jumps in the code. So by doing this transformation, this transform into SSA, we also do control flow analysis. By way of doing this, we simplify the representation of the code in a control flow diagram. The control flow is essentially represented as edges between these blocks. And blocks is essentially sequences of instruction where there's not a jump, because the jumps are actually represented by edges. Then the instructions inside the control flow diagram, inside this basic block, are written so there is only a single assignment on the left-hand side of the expressions. This is what is called a single static assignment, and that's what SSA means. The reason why we do this transform is essentially to simplify analysis later. I won't go into the details because this is really textbook stuff, but this suffices to say that then the optimization passes that comes after that are done directly on the SSA. So for instance, let's see an example. Let's say you have the C program where there's a if expression, there's if statement with a debug statement, debug constant that evaluates, let's say, to 0. That means that this block will never be evaluated at runtime, and we know this already at build time when we analyze our code. So this block can be essentially removed. This is called dead code elimination. We can do some other kind of optimization passes. For instance, this expression here, a times b divided by 2, we know that essentially b, in the context of this expression, can only have the value 6, and a can only have the value 5. So essentially, we can replace those symbols, those names, by their actual value and evaluate those constants, this expression at build time. This is called constant propagation and constant folding. And essentially, by doing these transforms, we replace the entire body of this simple function into the single return statement with a constant, because the value we know it's already 15. Now, once you have done a bunch of these optimization passes that might eliminate code, but also blow up the size of the code for optimization reasons, we can pass to the backend phase. In the backend phase, we replace all of these pseudo instructions into proper instruction for that architecture. In the case of ARM, the mapping in this case is pretty trivial, but it might be instructions that are mapped onto a number of sequence of instructions. So this is called instruction selection. You might notice that we have these weird identifiers here. These identifiers represent register, but they have a very large number, like 132. Why is that the case? Well, in ARM, we have plenty register as compared to MD64, but it's not a lot really. Still, it's plenty as compared to MD64, but it's still a finite number. It's 30 general purpose registers, so integer registers, and 32 floating point vector registers. So it's plenty, but it's a finite number. So in a large program, in a fairly common sized program, you might easily exhaust your reserves of registers. So what you do usually is you think like you generate code as if you had an infinite number of registers, and then you try to fit the reduced number of registers that you have into those registers that you actually have. And then you spill values to the stack when they don't fit, and then you restore them, And this is how your code will look like after register allocation. Finally, we finalize our code, essentially generate the epilogue and prologue of your function, as it would look in assembly code. And then we are ready to encode this code into a byte array. So we encode every single instruction into the representation in machine code, essentially. Now we have a byte slice that represents our code, and we are ready to execute it. How does that work? So this is can be different across different compilers, but more or less you need to do the same. Essentially, once you instantiate your module at runtime, you want your user to be able to call that code. But you have to respect the conventions of your platform. So in order to do that, you have to jump into the execution of the code. And to jump into the execution of the code that you generated, you have to use what is called a trampoline. And that's usually something written using assembly language. This is also true for Go, because you're able to do that. In the trampoline for the Go language, we make sure we don't fiddle with the register conventions of the Go runtime. So we stash away those registers, and then we restore them when we leave the execution of the code. This might happen when the function normally terminates, but also in the conditions of error. For instance, if there's a trap or an error code, we return from Wasm with an error code. We interpret that code, we give it back, we transform it in some way so that it's interpretable from regular Go code, and then we give back control to the Go runtime. But interestingly enough, this is also what happens if there is an OS function call. If we call an OS function, we return from native code, we restore the registers, and then we invoke the function that corresponds to the exit code that we have set in the native code. So every host function is assigned a specific identifier, and then we look into a table to find it and execute it. Once the function returns, we get the return code, mash it in the way that native code will, the code that we generated will use it as expected, and then give back control to executable code, to the executable code we generated until we actually return. So now let me spend like 5 minutes on chicory. I'll go faster here. Yeah, I've been going around and telling people that Wasm is not the same as the JVM, and then yet I'm talking about the JVM runtime for Wasm. When it comes to limitation in with FFI, the foreign function interfaces, Seago is pretty much similar to Java native interface. It's different in the user experience, in the developer experience. The code you write is different. It's more cumbersome, but the limitation about portability, playing nice with the garbage collector and the threading system, it's really just the same. JVM bytecode, on the other hand, is kind of similar to Wasm to some extent, to the point that this expression, you can really literally put them side by side and it will look exactly the same. As for control flow, they're kind of different. In fact, this is Java bytecode, and as you can see, it has conditional branches and unconditional branches. Well, Wasm actually has structured control flow. It has ifs and then else, and it has loops, it has blocks. And this is to make it possible to validate more safely the code, to make sure that the code does not go crazy and you know, it's easier to validate. So that's another way Wasm is safer than other code representations. So Chicory comes with an interpreter that's really easy to hack because it really follows the Wasm bytecode representation, the Wasm bytecode spec. And so it's very easy to follow and hack, and it's not meant to be fast in any way. It also comes with an AOT compiler that translates Wasm bytecode into Java bytecode. And as you saw, there's a really close correspondence between them. We have an online runtime bytecode generation that does class loading, which is pretty conventional technique to generate and execute bytecode at runtime in the JVM, and also an offline version that generates bytecode on disk. So essentially, you have this API to load the code, to load a machine, and the machine might be an interpreter machine or an AOT machine. We can skip the interpreter part. But the way the AOT version works, the compiled version works, is that essentially we translate at runtime Wasm bytecode into Java bytecode. And the cool thing is that the processing is really simple because of how close they are. Essentially, all we need to do is rewrite in the control flow because they're both stack machines. So we rewrite the control flow as to use the unstructured control flow that's provided by the JVM, and then they work pretty much the same. We generate classes, and these classes are loaded just as much as traditional classes. And the cool thing is that we can also reuse a lot of code from the interpreter itself, because we don't really need to rewrite the functions that implement the opcode, because we can rely on the JVM to inline that code. So a lot of code is really reused. And function invocation is essentially just initiating the class and then invoke those methods, because that's just regular Java methods. And you can find online some comparison with Growl Wasm, which is a state-of-the-art Wasm implementation for the JVM, and you will see, we don't have time to go through these, that performance, especially for the AOT, well, specifically for the AOT version, are really comparable in the same ballpark, and we didn't spend even a lot of time into making that efficient. I also wanted to mention that Chicory in the interpreter flavor works on Android. This is mcp.run running on a device. It's just pretty cool. Just the interpreter without any specific changes works on Android. AOT needs a separate discussion because AOT, the offline AOT works because it just translates a build-time bytecode. So the regular Android toolchain can translate that Java bytecode into Android bytecode. But it's also working on a runtime on-the-fly translation, which is useful for plugins, obviously. And we have reached, we are passing now all of the spec tests that are available for current Wasm. And it is interesting because Android is a register machine, so it's not the same as the regular JVM, so it requires a different compilation pipeline. So yeah, still we reuse a lot of code, and it's pretty awesome that it already works. But there's a lot of work to do. If you're interested in Android, in the Android backend, just let us know. This is internal for now. But the rest of what you've seen is open source. So please check it out and hope you liked this presentation. That was all I had. Thanks.
Thanks a lot, Edoardo. So it was a really nice talk, and I think, by the way, please let us know how do you evaluate this talk. And of course, at the moment we are having Q&A session, so I think we will have it on YouTube, and also it will be transferred to our internal channel as well. So we'll give like several minutes. But thanks again, of course. I think everyone enjoyed it. At least me personally, I did enjoy it.
Appreciate that.
Great, great. So we are expecting some questions right now. And also, guys, I mean, for those who are watching us online at the moment, please let us know on your thoughts in general. It shouldn't be only questions, but also if you have something to share with Eduardo, for example, some feedback, whether you like it, whether you have something to add, we would also appreciate your opinion, because, you know, it's all about communication, right? This is actually the point of Meetup. So yes, please don't be silent. We are expecting to see you. So yeah, I can see several questions. It was now transferred to our chat. Eduardo, can you see them?
I do. So there's at least two questions. So
At
one
least.
is, how does Wasm compare to Java? Why one should choose Wasm today over JVM? That's a good question. Well, I think I have partially answered already with a talk. We've seen together. There's JVM. Actually there's at least two WebAssembly runtimes. I mentioned Chicory because we work on that. But there's also Truffle Wasm that runs on the JVM. So Wasm, it's kind of different than the JVM. On the one end, Wasm is something that can be embedded very easily. The JVM is somewhat larger, so it's not as suitable for embedding as the JVM. It's also lighter weight in many ways. The runtimes tend to be smaller, and so it's a lot of companies are using it to provide a runtime environment for serverless functions as a service, so for cloud functions, so to speak, because it's a good place. It's a good alternative to containers in that sense. Why would you choose it over the JVM? Well, the answer is you don't really have to choose. I think that they have different goals, and in some places those goals overlap. Obviously, you can write serverless functions on the JVM. Why not? We did that for a while before we started all the container craze. But yeah, and you can also use the JVM to run Wasm. So you can host and write extensions and host them inside a JVM runtime. And by the way, you should also stay tuned, because there are runtimes and compilers that will allow you to compile Java to Wasm. So you will be able to run your Java code on Wasm runtimes. So you will be able to run your Java code in places where you couldn't before. So I don't think there's really a competition. They're similar, but they're different. I think partially we've seen how they differ. Yeah, I think they're like another tool in your tool belt. You will reach out for one or the other depending on the use cases. I see there's also another question.
Yes, yes. Thanks a lot, Eduardo, for answering this one. Yes, let's take the second one, please.
Sure. So the other question is, how do you deal with the need to share memory between host and guest without copying without them? So imagine something like video processing plugins that work on raw frames. All right, so that's a great question. There's a lot of ways. The question, I don't know if the question means that the person asking is already aware how Wasm work. Maybe it is. So Wasm, at least in the first versions, they did not have a way to share memory with the host, not directly. I mean, it comes with a large array that's called the linear memory that essentially behaves like native memory and often is mapped onto native memory. However, in order to write code that is interpretable by the Wasm guest, the Wasm code, you have to serialize data to this memory, and that means that you will have to do a copy, obviously. So there are at least two ways to avoid doing this kind of copying. First of all, you as a developer can write your own host functions, as we mentioned earlier. So these host functions are allow you to do anything that your host language, your host runtimes can do. So one way to avoid doing copies is essentially to provide an access, a direct access to the code, to the data that you want to share with the guest. So let's say you have a frame. So the way you would share it with the guest is by providing a function that allows you to take slices of that frame without copying it. So you can access single pixels, single bytes from the data frame. So you will provide a function, let's say get byte, a function get slice of bytes, and so on and so forth. So you can only access those bytes that you really need. Another way that is more recent, it's something more, new addition to Wasm, and it's available already in the browsers, and it will come to the other runtimes in some time, I guess. This is the GC spec. The GC spec is not just about garbage collection, it's about sharing data with the host. So what garbage collection in that sense means is that you have now a way to describe the structure of your data, in Wasm. And then you can point Wasm to that structures. And those structures can live in the memory of the host. And that means that then the access, you can give direct access to those values and essentially tell the Wasm runtime that the host will manage the collection that is freeing those values. So that's another thing that will definitely allow you to avoid that.
Okay, thanks a lot, Edoardo. And I think we've got one more question. I think it is connected somehow to the previous one. So basically, it is the last one in our chat. So good question, some kind of DMA for the WASM runtime. So this is the question. I think
DMA, the kind of DMA for the Wasm runtime. I don't know what they were referring to though.
Okay,
I guess
maybe it's like
yes is
some kind of
probably the question.
conversation. Yeah. Okay.
I guess it's probably the answer in a way.
Okay, guys, if you have any more questions, please let us know because we are still having time before the break for the Q&A. We wait for a couple more minutes. And then we will have a short break for 10 minutes approximately, and we'll pass it to our next speaker. So let's wait for another couple of minutes.
Meanwhile, I just want to spend one extra nice word about tech internals because I've been to one of the past editions before it was even called tech internals, and it was a really enjoyable experience. So I promote.
Thanks a lot, Edoardo. Yes, we are trying our best. And of course, we really appreciate the contribution of the speakers like you when it comes to our events. And it's like super nice that you support us with this amazing meetup. So by the way, we have like another 1 minute maybe to wait for the question. So by the way, where are you now? What is the weather like? So it's like a traditional Zoom conversation right before the real job starts.
Yeah, it's it was kind of sunny enough today. I could go out for a run, but it's been rainy for a few days. So yeah, it was
Okay.
nice for a change.
Great, great. Okay, so if we let me just double check with my questions. I think we don't have. Yes, so the person in the chat said that I think they have already answered my follow-up in answering the previous question. Thanks. And also, we don't have any more questions. So thanks a lot, Eduard. again for your amazing talk. So everyone, please follow Eduard. We will exchange some contacts. So if you have any more questions, we will forward them to him. And now we are having the short break, approximately for 10 minutes, and then we will go to the next topic by Vlad. I will introduce Vlad after the break. So now let's grab some coffee, some drinks, and see you in 10 minutes. everyone. So we are back now after the break. Hope you had some rest. And at the moment, we are ready to proceed with our next speaker, Vladislav. Tell us his amazing topic. So Vladislav, now I would like to pass it to you. Please start. I think everyone is ready now. Thank you.
Okay, let's start. So my name is Vlad. I've been writing code C, C++ for 10 years, approximately by now. During this time, worked with databases, games, advertising, and in all those areas, I've done a lot of work with networking. I have seen various problems, solutions, some of which I created myself, including problems, unfortunately. And today I'm presenting an algorithm I have created for what I believe to be quite efficient networking, implemented in C++, but suitable for some other languages too. Something you have not probably seen before, not necessarily in a good way, in the sense that the same solution can be worse and best different contexts. Nonetheless, I found that my specific algorithm turned out to be noticeably better than what I have worked with until I created it. And I want to emphasize today that our focus will be on the algorithm itself and some of the details, but not on the implementation. There is not much point in that, to be honest, because existing projects are unlikely to switch their networking stack to a new library, no matter what library it is. And new big projects don't come up that often, but I believe that spreading ideas is useful. So perhaps mine will seem interesting enough, someone could apply it in their code, not necessarily taking my implementation. The algorithm is simple enough to implement it yourself, so you don't have to rely on my implementation. The focus is the algorithm. And the plan of the presentation will be the following. Firstly, we see what we have available for networking and C++ available out of the box, then existing solutions for massive networking, then we see the new algorithm, how it looks like, why was it needed, we see some examples of the code, and then I show you benchmarks. Let's ask the toughest question, I would say, why even write networking code in C++ when in the modern world we have Go with Go routines, Java with virtual threads, Rust with Tokyo, and probably many other good combinations, but those three are good enough to make C++ obsolete, in my opinion. And I have seen the following reasons, specifically why C++ is still alive in backend networking is that firstly, system is already in C++ and its rewrite is unrealistic, quite a frequent case. Then development teams knows C++ exceptionally well, and they are willing to start new projects in it. And the last one is that you need the best performance. All the other solutions, they are good, but they are not as good as C++ when it comes to perf, if you know what you're doing. And today we focus on the last one, because the others we cannot affect anyway. Let's say that we decided to go with C++. And what does it offer us for networking in terms of work with sockets? I mean, like send, receive, connect, accept, and so on. Those basic things. Out of the box, we don't have that much. We don't have many more than what I just listed, actually. We have the standard C library, which has those basic things. Also, each platform will give you its own technologies, like KQ on Mac, IPFOL and IOU Ring on Linux, and IOCP, IO Ring on Windows. They are all used for massive networking, but the problem is they come on top of the other basic API like sockets and receive connect, and they are not standardized. So if you start using one of them, it will only work on that platform. If you, for example, implemented your backend in KQ, you have to use Mac or FreeBSD. Or you have to support all the others too. And besides, those APIs, they don't really look very well. They are very low level, require a lot of boilerplate code to write, and they are very C-like. Lucky for us, there are many projects that wrap those two low-level things into convenient C++ wrappers. There are not that many, actually. If we talk about proven, popular, and flexible solutions, then it's just a handful, actually. I can name you just a few known to me. First, you all probably know anyway, it's Boostessio, of course, provides tools for asynchronous I/O. It's very old, stable, efficient, has a community, it's tested in countless projects. Relatively easy to use once you grasp the key ideas like what is a strand, what is a context. Once you understand those things, it becomes very easy to write networking code. And it is de facto standard for asynchronous I/O. It's the default choice, what you take when you just want to write good enough asynchronous networking code. You will see Boostessio in resumes as a skill and in job descriptions as a requirement. Another project is uServer. It's a backend framework, not just a networking library. It includes coroutines, connectors to popular databases, coroutine friendly even, and some like many more other stuff. Also, we have C-Star. It's a project from ScyllaDB, which initially was created for that database, but eventually it became standalone project used for backend development. And of course, we have some smaller things or less related things, so to say, like Thrift, gRPC, libf, libuv, libevent, protobuf, or whatever things in this area. And if those solutions are so cool, then what are we doing here today? Just use Boostessio, and I'm going to be completely serious here that just use Boostessio when you can, because it will cover everything. Probably it has a lot of tutorials, community support. Parts of the library are likely to be included in the C++ standard, which will simplify updating your code in the future. But the problem is not always like, yeah, for 99.99% of cases, Boost will do the job. But you have the remaining 0.001% of cases which are the most challenging, and when you cannot use Boostessio, or you can, but it's not good enough, and any other solution as well. Specifically, the ones I listed so far. Boostessio code, it's unreadable. I hope it's not just me. Boost code is in general very hard to read, but Boostessio is the next level of something that is completely impossible to understand, and then its performance is very questionable under serious pressure. If you take uServer, it has no Windows support. Take C-Star, it has no Windows, no macOS support. It's Linux exclusive, basically. And then if you take Thrift, gRPC, they enforce their own protocol. And solutions like libf, libuv, they are C or they are single-threaded. It all doesn't really work. And the biggest problem, which makes all the others irrelevant, is that it could be that your company lives in its own framework. It has its own library of everything, and you just cannot take anything else. You are lucky if you have the standard library available, but it's not always the case. In my experience, I did when I worked in game development, we had this problem that, well, not really a problem. We had this thing that company had its own library, and we were not able to use even the STL from C++. So this is when I implemented my own algorithm in C++, and making special focus on simplicity of the code and of the API, because when I worked in that company, it held a lot of junior developers, and they were supposed to understand the code and to be able to maintain it after I'm gone. So the code is actually quite simple, and the algorithm is not challenging to understand. At least I hope so. Before we proceed to the algorithm, what did I want for this algorithm to provide for me? Firstly, I wanted it to be fair, meaning that I want uniform utilization of all the CPU cores. It means that I cannot bind tasks and sockets to specific threads, which some schedulers do, but it's not a good idea in a general case. In my specific case, for instance, I had tasks like clients connecting, and the workload different clients were requesting was varying from microseconds to hundreds of milliseconds. I could not afford to pin sockets to specific threads, because eventually I would have many sockets keeping one thread super busy and other threads being idle. So that just doesn't scale. Then I wanted coroutines, or in other words, I wanted specifically cooperative multitasking. It's a bit wider concept than just coroutines. And one feature which I needed from cooperative multitasking is to be able to pause tasks. So when task is waiting for something, it would step off the CPU core instead of keeping the thread busy, and the thread could do some other tasks. And then I could have, like, I don't know, 16 cores, 16 threads, and millions of tasks running concurrently. And last, I needed events, which is directly connected to the coroutines. The thing is, when a task is waiting for something, it's sleeping, and the thread is doing some other tasks in the meanwhile. I want to wake the task up when some event happens, what the task was waiting for. I want to wake it up, so it gets scheduled in the thread again, gets executed, and it can proceed. All of this I managed to satisfy the algorithm which I called task scheduler. It's just a very simple name. Neither the algorithm itself nor the code are very much complex, as I mentioned, but we will not delve into details because we don't have much time available. I will only show you the big picture with broad strokes and some code examples and some examples how the algorithm is working. For slightly more details, you can check out one of my past talks, and you can ask questions, obviously, after my presentation. Besides, the code is very simple and short, so you can just go and read it. It's open source. You can go check it out. It has a lot of comments. Like, there are, I think, more comments than code, actually, and a couple of huge readmes. But let's proceed to the algorithm. Imagine that we have a process, and it has multiple threads running in it. Sorry. Imagine that we have a process, several threads running in this process doing different work, and one of them has a TCP server that is accepting sockets. Each socket we wrap into a task. And when tasks want to do something like read and send data, execute your callbacks, wait for timeouts, and so on, they are sent into the scheduler. And there they will go for a pipeline. Firstly, they will enter the front queue, the first step of the pipeline. Most tasks usually are not ready to get executed immediately. They want to wait for an event. If we talk about networking, then usually task wants to wait until its socket becomes readable. Right? Most of the time sockets are not readable. You need to wait until it becomes readable, then you can read it. Or a task wants to wait for a timeout, or for an explicit wake up, or for whatever else. The point is, a lot of tasks are not ready to get executed, so they get moved into the waiting queue, and they will stay there until get woken up, or their timeout expires, or their socket gets an event from the kernel, like it becomes readable, writable, whatever. And this queue already had, at this stage, probably some older tasks from the previous pipeline runs, which are still there, but they could be ready now. For example, from the previous time, there was a task which wanted its socket to become readable, and now it became readable. Or a task had a deadline, and now the deadline is expired. Those tasks, plus the tasks from the front queue that did not any waiting at all, they all move on to the ready queue. And now they need to be executed by some thread. So to actually do the I/O, to execute your code, set new deadlines, and whatever else they would want to do, for that the scheduler has several worker threads. They will take tasks from the ready queue and they will execute them. Some tasks are complete and they get removed, deleted, whatever, like socket is closed, for example. Then you just don't need to work with it anymore. Other tasks, like most of the time, they will go back to the scheduler through the front queue and will continue working. So for instance, if you read a socket, you usually read it, maybe send something, then you read it again and again and again, right? So the sockets usually are like being read in a loop of some sort. So the tasks, most of them will probably go back to the front queue and go through this pipeline again. This is the whole algorithm in very broad strokes, but the essence is all here. Now let's have a look at a couple of particularly interesting details, in my opinion at least. Firstly, who does the scheduling? Like, as you can see on the slide, the tasks are being moved from the front queue to the waiting queue to the ready queue. But who is doing the moving? Like, you need a thread to do the work, right? And in scheduler, it's done by one of the worker threads, but not a fixed one. Instead, the threads, like the worker threads, they will occasionally compete for the right to perform the scheduling. You can imagine that like this scheduler is a castle, and the threads try to take the only key to open the gates, and whoever takes the key enters the castle, does the scheduling, leaves the castle, and proceeds to the task execution. And any worker can pick up the key, depending on who of them is free right now. Let's look at an example, like just some specific example with some specific tasks. I find it most useful to understand algorithms as examples. Imagine that we have 5 tasks, and we have 3 worker threads, and one of the worker threads picks up the scheduling key, and it goes to the scheduler. Here it will wait until something appears in the front queue. Finally, 5 tasks enter the front queue, and the scheduler will notice them. It will check them out. You will see that a couple of them, let's assume, are waiting. They don't have stuff to do right now. And other tasks are ready. So they're moved to the ready queue. And a couple of worker threads, the other ones, they will start execution of those tasks. And the third worker who was doing the scheduling will join them. Eventually, a couple of tasks are done. And a bit later, we noticed that a couple of waiting tasks became ready. They need to get executed ASAP. They could become ready due to any reason. Maybe somebody woke them up. Maybe their sockets got some events which need processing. Anyway, the point is we need to move them to the ready queue somehow. After a while, one of the worker threads will enter the scheduler, and it will check the status of the waiting queue. It will see that a couple of tasks are ready. It will move them to the ready queue, and other workers will start executing them. Eventually, those tasks are done, and all the tasks are completed now. We have 2 workers waiting on the ready queue and 1 worker waiting in the scheduler on the front queue. And this process will get repeated as long as the scheduler exists. Then how does task wake up work exactly? I mentioned it a few times by now, that task gets woken up explicitly or by socket or something. How does task wake up works? For example, imagine we have a task in a waiting queue, and it's waiting for a deadline or for some event. And when event occurs, I need to wake the task up before its deadline. To be more specific, let's imagine we have a task sent an HTTP request, and it wants to get woken up either in 10 seconds or when the response arrives. 10 seconds would be like a timeout. If the timeout expires, I want to treat it as an error. So request timed out. It's not so simple if you think about it. Imagine that we have very many tasks in the waiting queue. We have millions of tasks. They probably have a deadline, but it's very far in the future, or it's even infinite. It is also possible. And we have just 1 worker thread to handle them all. What will happen while none of the tasks are ready or woken up is the thread will sleep in the scheduler until the nearest deadline happens. You can, if you store tasks in the binary heap, for example, you can always tell which one is the closest, which deadline. So it sleeps on the closest deadline until deadline expires or something appears on the front queue. And the problem is not only you have to wake the thread up, not only you need to wake the thread up, for example, through condition variable notify or something like that, but you also have to inform the thread which specific of those millions of tasks need to be moved from the waiting to the ready queue. And regardless of what is the data structure you use for the waiting queue, binary heap, array, tree, whatever, you cannot possibly full scan it on each scheduling pass to check out which tasks are ready. It has to be done somehow faster. And here I use a small trick, which perhaps is the most untrivial part of the scheduler. To simplify, I send a special marker to the scheduler through the front queue. And one marker corresponds to exactly one task. Those markers, they enter the front queue, just like tasks. And the scheduler will get woken up by that. And it will match those markers to specific tasks, will take them out of the waiting queue and move them to the ready queue. And then it can start executing them. This way, I can use something smarter than just a full scan of array for the waiting queue. And this mechanism I use quite widely. It's not just for explicit wake-ups. It can, like I do, you also use it for waking up the tasks when their sockets get events from the kernel. For instance, on Linux inside the scheduler, I run epoll or ioring, and when kernel delivers me socket events, I wake the tasks which are having those sockets using the same algorithm. What about implementation of this thing? The code is quite minimalistic. It's less than 2000 lines for the scheduler, including comments, empty lines, and formatting specifics, so it's not really that much. It is almost entirely log-free. It has just 3 mutexes taken very rarely. It doesn't require much memory. One task will cost you less than 100 bytes, and the algorithm is formally verified in TLA+. I had to do it to be confident in the conceptual correctness of the algorithm, so I don't have any deadlocks, infinite loops, lost tasks, double execution, or something like that. Some logical mistakes. In case you don't know what is TLA+, it's a mathematical language which has runtime, and you can write your algorithm in form of mathematical formulas. And then you describe invariance of your algorithm also as mathematical formulas. And then runtime of this language will make a full scan of all states of your system and check invariance on them. And then you can see if it's conceptually correct, your algorithm. Speaking of the platforms, I support for this implementation C++ 17 and above, compilers CLang, GCC, MSVC. For Windows, I support IOCP, IO completion ports, for macOS CACU, and for Linux epoll and ioring. And architectures, you can run it on x86 or ARM. Out of the box, it already has implemented TCP client and server with optional SSL support based on OpenSSL. Let's see some code examples. They are all runnable, by the way, by the links on the slides. You can open them and compile and run and so play with them whatever way you like. Let's start with the simplest one, just task scheduler itself. It can execute tasks without sockets, just plain callbacks. And here I create a task scheduler directly on the stack and posted a task into the scheduler. And the task body is a Lambda function that prints something and deletes itself. The task will get executed on the scheduler's worker thread and will print something and we will see the output. This is a very simple example. Let's make it more interesting. Let's add multiple steps, not just one. Specifically, in my example, I want 3 steps. And between those steps, I want to release the thread to work on other tasks. Or in other words, I want to do coroutine yield to leverage this cooperative multitasking idea I was talking about. Moreover, I might want to have context in my task. For instance, if we speak about business logic request as a task, then you might want to have their data, like parameters of your request, credentials, URL parameters, headers, whatever else you might need for your business logic execution. In my example, it can be done in a few ways. In my example, I inherit the task, and then I can add context as members of this new class. But also, you can do it in another way. For example, you can use Lambda C++ captures to capture some context in another way. You don't have to inherit it all the time. You can also use task as a member of your class, along with any other members having your data. Again, it doesn't have to be inheritance. And I have here 3 steps: send request, receive response, and finish. Let's see how I can define them. The first step, send request, will print something, change the task's callback to step 2, and will post it further. In this case, the task will get reposted right away, get rescheduled because I didn't set any delays or deadlines, so it will just be executed again after going through the front queue, waiting queue, ready queue. And the second step will be the callback that I set on the first step, receive response, which will again print something, set its callback to the third step, and then will post itself again. And then on the third step, I just print something, and that's it. You can here do whatever you like, actually. You can reuse the task, you can delete it, or anything else. In this case, I just don't do anything because the task was allocated on the stack. I don't even need to destroy it explicitly. And the previous example, though, it did not look very well because of the callbacks looking a bit messy. At least in C++, they don't look very nice. When you have to set callbacks, which sets another callback, which sets another callback, it's looking ugly, really. But luckily in C++20, we have coroutines introduced, which we can try to use to rewrite this example. Here I again create one task, which has a body, which is a coroutine. And in case you don't know, in C++, standard any function becomes a coroutine as long as inside you will use co-await or co-return keyword. And the function has to return a promise object, which is basically coroutine object. In this server box project, it already is defined as mgbox cora, so I don't have to define it manually every time. It's quite messy to define them, to be honest. And now inside of this coroutine body, I can use co-await on some built-in scheduler operations like async yield, async wait, async receive signal, some others. Async yield is very simple. It will just yield control to other tasks yield control to other tasks. So it will put your task to sleep, some other tasks will get executed, and then your task is scheduled again. Between the yields, you can do whatever you like. Here I am just printing stuff, same as in the previous example. Now, less complicated further. Sometimes, I would even say most of the times, tasks need to interact either with each other or with some other subsystem. For instance, let's imagine that we have a task that creates work and goes to sleep, and I want this work to be done asynchronously by some other task and wake the first one up when the work is done. Let's imagine that we have a function that creates this asynchronous work, task submit request. It creates, well, in my case, I do it this way, but you could pre-allocate this task and reuse it or something. In this case, I create a temporary task on the heap, which will simulate work for 1 second, and then will wake up the creator task via post signal. So the creator task can be woken up, and it will see that the work is done, the result can be processed, whatever the result is. And now let's try to use it. So here I created a task which started asynchronous work in another task, and now it waits until it's woken up with the result. Again, as a coroutine, but this time I use async receive signal to wait until the other task will wake me up with this signal thing. Now let's add I/O. After all, this talk is about networking and not just the abstract scheduler. For this, you still need a scheduler, but a bit more complex one, I/O core. Its tasks have sockets, that's the difference. And the tasks are very similar to Boost SEO strands, if you are familiar with the thing. If you are familiar, it's basically almost the same one. Yes, strands. Let's start with the main function. I here create I/O core scheduler with 3 worker threads. Then I create asynchronous TCP server, which will listen for incoming connections, and it is implemented as a task. And then I start asynchronous clients. Each of them is also surprisingly a task. Let's have a look at how the server is implemented. The server I have to inherit from TCP server subscription. Via virtual methods of this class, I will receive events. In case of TCP server, there is not many events really. It's just when new client gets accepted and when the server gets closed. So just 2 events. And the server is this TCP server object, which I have to create by giving it I/O core in constructor. So it will work in this I/O core. But the server is not started yet. It's just created. It's not yet in I/O core. And it doesn't yet run and accepts clients. To start doing this, you have to call bind firstly. Bind to specific port or to specific host and port. In my case, I just do it to port 0 to get random port assigned, and then I can get the actually assigned port. So the clients could connect to it. And after bind, you call listen, and from the moment you call listen, the socket will run in your core and will start delivering events. The most interesting events that you can get from TCP server is on accept. It is called when a new socket gets accepted. So accept itself is already done by I/O core. You just get delivered the socket, which you can use for I/O. In my case, I simply create a my peer object with the given socket, which will asynchronously read and write the given socket. And when the socket gets closed, the peer will delete itself. The peer is implemented almost the same way as the client. So let's just have a look at the client to save some time. This is how I define it. I have to inherit it again from TCP socket subscription this time. And this class has many more virtual methods compared to TCP server subscription, which will deliver me events like on receive, on send, on connect, on error, on whatever else, on close, right? Also, this client creates the socket in a similar way like the server did. So I have to create TCP socket object by giving it the I/O core in which it will run. And then I have to firstly open it. I can provide here some parameters, but I don't need to in this case. So it's empty parameters. And then I want to connect. To connect, you have to fill up the connection parameters. In my case, it's just one, the endpoint, where I specify the endpoint as a local host with the given port. You can also use here domain name. It will be resolved to IP address anyway. And then I start connecting. From the moment you call post connect, the socket is living in your core and it will start delivering events. The first event you will get delivered is on connect. And in my case, on connect, I just immediately send the handshake message to the server and I receive asynchronously 1 byte as a confirmation. So the sending is also asynchronous, by the way. And my logic here is that the peer, when it will receive the handshake completely, it will send me 1 byte back as a confirmation. And when I receive the confirmation, I just close my socket, and then closure is also asynchronous. And when it's done, I can safely delete everything. On close, I can be sure that the socket will not be running again anywhere, so I can delete it safe. Or I can reuse it. You don't have to delete it. It's very handy when you want to do reconnects, like automatic reconnect once per second or something. It's actually quite easy to do this way. Now, as you can see, we have 2 schedulers here. IO core and task scheduler. It's not just one. And IO core actually can do pretty much everything what task scheduler does, almost. It's just IO core has a bit more overhead because it obviously has to do more actions. For instance, on Linux, it also has to run epoll internally or IOUring, right? It's just a bit more work. Also, IO core tasks need just a little bit more data, so the overhead is slightly more than for task scheduler. And the most efficient setup is that you use task scheduler for high-level business logic requests, which do not do direct IO, and you use IO core for doing the IO itself to work with the sockets, and then they can cooperate, those schedulers. Let's see an example. And for our example, I designed this like challenge. Imagine that we have a front-end client-facing server that accepts user requests, and each request wants to execute a simple arithmetic operation like a plus b, c multiply d. But my server, this front-end client-facing server, does not know how to do mathematical calculations. Let's just imagine it can't. Instead, I have to send the operations to an internal microservice which can calculate them. So my user business logic requests have to do sub requests to some host calculator backend server. For this, I firstly have to write a calculator client, which will asynchronously talk to my calculator host. And I called it calc client, and it's just implemented as a TCP socket. It has a single public method which submits asynchronously an arithmetic operation to the remote server. Operation, arguments, and when the response arrives, it will invoke completion callback with the result. It's not that hard to implement this thing. It's done completely using IO core, TCP socket. We will not look at it right now. It's very similar to what you saw before. We're more interested in cooperation of IO core and task scheduler right now. And my business logic request will be that I call it my request, and in constructor, I will give it the asynchronous calculator client and the task scheduler object in which it will run. And it just immediately posts itself. So it will start running SAP. And its body will be the execute method, which is a coroutine. The code is very simple, really. So here I submit the operation to a remote server, and I wait for the completion. While waiting, I am yielding control to other tasks until I get explicitly woken up by this request being complete. I use here, as you can see, async receive signal with co wait. So I'm yielding and the thread can do other tasks while I wait. Eventually, my request is done, response arrives. So I save the response in my completion callback and I wake my task up by using post signal. And this will wake the task up. Async receive signal will be successful and I can handle the result. In my case, I just printed. And done with the task, I can do whatever. As I said, you can delete it, you can reuse, you can do more operations in a row, whatever you prefer. And this creates a symbiosis of task scheduler and IO core. You use the first one for business logic handling and the second one for talking with the network. Algorithmically wise, I would say the IO core and task scheduler are identical. So they just do the same stuff. It's just implementation-wise, IO core is just a bit heavier because it needs to work with the sockets, while task scheduler does not. Finally, let's have a look at the benchmarks. Perhaps my stuff is very slow, and then why do we even need to use it? My main goal with the benchmarks was actually that it should be very easy to run them, very easy to read the results. Firstly, for myself, because when I optimize something, I want to see the result, how new stuff became better than the old stuff, and I want to do it fast and easy. And secondly, for the users too, so you can run those benchmarks on your specific hardware to see how does it perform there. And the benchmarks, because of simplicity requirement, it can be run with a single Python command, which takes configuration as a JSON and runs certain scenarios. It will like literally run binaries of compiled C++ code, will generate a markdown report, which is very easy to read. You can find them on GitHub. They are all already there. And then you can see what was faster, slower, by how much, what was RPS, latency, mutex contention, and so on. Medians, maximum, minimum, whatever other metrics there are. And also benchmarks are comparative, meaning that I don't see much sense in just running benchmarks on their own. Like IO core can do 1 million messages per second. Is it good or bad? I don't know. Depends on the hardware. Depends on the scenario. It's too many depends. And but it becomes much clearer when you compare things. Like you compare IO core with boost ratio, and then you can tell if your stuff is good or bad compared to something which already exists. As a starter, let's compare task scheduler and just a regular thread pool without coroutines, timeouts, waiting queue, ready queue with all this overhead, with just a task queue with a mutex, callback queue and the mutex, nothing else. Seems like it should be fast because it doesn't do any of those extra steps. And there are many scenarios of those benchmarks. I run them on different hardware, different systems, but within our time constraints, I have to show just a few of them. The first one is tasks are empty with nothing in their body, so just empty callbacks. It's not very realistic, but it's good to test how much is the overhead of your scheduler. Like how much does mutex contention or thread contention affects your performance? Because all the time you spend on doing tasks, you actually spend on doing the scheduling work because tasks are empty. And the second scenario is when tasks do something for a few microseconds in their body. Everything else is the same. Then overhead of the scheduling per task becomes significantly lower. It is more a realistic case, actually. And we can see the task scheduler was always much faster, up to 100 times faster even. Specifically on 50 threads, it was still able to deliver millions of tasks executed per second, while the thread pool with just a mutex and a queue degraded to tens of thousands per second. All those results and any more you can see on the link on the slide. It's all already posted. For IO benchmarks, for networking, the most interesting comparison for me was between IO core and boost ratio. I used in my benchmarks the latest version of Boost, which I had at the time of implementing them. It was 184, so it's like really fresh. And as a backend, like the actual kernel backend for getting the events from sockets, I used 4 technologies on 3 operating systems. And there are, again, many scenarios which do all the same thing, but they are different in parameters. The template of our scenario is echo server. So client connects to server, sends a message, server sends it back. But you can vary message size, number of messages in fly, message complexity. For example, you can increase number of integers in the message to make its decoding slow. or you can make a message huge, but with no content basically. So its decoding is very fast, but you can saturate the throughput of your network. So you can test a lot of things with this echo server thing. And we'll look at several combinations of those settings, which we have time for. Let's start with Linux with EPOL backend. We can see that IO core turned out to be significantly faster than Boost SO, which was even a surprise for me. To be honest, I expected from Boost better results, given how popular it is. Then I was very curious about testing this new IO ring thing, which I do support in IO core, and I got the same results. IO core was much faster again. With Windows IO completion ports, again, IO core was faster. Not always, though. There is one case, to my shame, where IO core was a little bit slower. We can talk about it after the presentation, whoever is interested to, which scenario it was and why did it happen. And macOS with CAQ, again, IO core was faster. You can see it was an old Mac, so just 4 cores. It's a 10 years old Mac, basically. But I did run it on newest Macs too, on M processors. It was also faster. I just didn't update the benchmarks yet. And in conclusion, I wanted to invite people to discuss a topic, like after the presentation directly or in writing. You can contact me and we can discuss it. A problem where all the user space will get united for a shared problem. What to use, EPOL or IOU ring? IOU ring is this new fancy thing, which is super fast, supposedly, and EPOL is old, supposedly slow stuff, which is very hard to use. And you can see a lot of hype around IOU ring being replacement of EPOL. In case you don't know what they are, EPOL allows you to subscribe for events from many sockets, like millions of sockets. Well, I didn't test millions, tens of thousands, easy, yeah. Handle each event individually. So you have, let's say, 1,000 sockets, you get 1,000 events from the kernel, like those sockets are readable. Then you have to do 1,000 reads, 1,000 receives in separate system calls. In IOU ring, the point is that you send operations in batches into the kernel executes them and then sends you back when the request is already done. For example, you can, with IOU ring, send in a single system call or without system calls at all into the kernel 1,000 send operations on 1,000 different sockets. Easy. That's the whole point of IOU ring. It allows you to not have so many system calls, which is the most expensive part of like one of the most expensive parts of networking often. And you would expect that in the world where we live in after the meltdown, vulnerability was fixed, system calls are super expensive and removing them will give you a huge boost, which is not what I observed in my benchmarks. I saw that Boost and IO core, both running EPOL versus IOU ring, always were giving results with EPOL being twice faster. Like it's not a few percent, it's twice faster. I compared Boost EPOL versus Boost IOU ring. I compared IO core EPOL versus IO core IOU ring. All the same results. And you can see why IOU ring is not default in Boost, because it's just slower. And even on a single thread use case, which looks like should be the killer, like the best scenario for IOU ring, it still was slower, at least in IO core. In Boost, it was a little bit faster, but IO core was faster than Boost. So IOU ring did not give me any miracle speed up. And I have a theory why it could be this way. But I am curious if somebody has more insights into this than I am having. So, yeah, it could be an interesting discussion and an interesting holy war, like EPOL versus IUU ring. Thank you for your attention, and now I'm ready for the questions.
Yeah, thanks a lot, Vlad, for your amazing presentation. And now we are expecting some questions to our chat. So please leave your questions at the comment sections. Don't be shy. We are here to chat. We are here to network. So we are expecting your questions. And as soon as we receive them, I will forward it to our chat, Vlad. So I will let you know, okay, when we receive them. Yes. So also, what should I say? I don't think that I have to say anything. Let's just wait for the questions.
I see the first question. Yeah. Does the price include listening to
I
several?
think it's not
Ah.
referring to, yes, referring to, it's not referring to, yes, yes. We are now, yeah, if it is about TIC, Tech Internals Conference, yes, basically, you don't need to pay anything additionally whenever you purchase ticket for the conference. You are you can visit any talks, as many as you wish, and also you can take part in the Q&A zones, and also you can communicate with sponsors of our conferences, as well as take part in the networking party. And after we finish with our questions to Vlad, I again will share some information about tickets, about discounts, and so on. So let us again some questions to Vlad, please.
Okay, I see questions. The first one, why do you think in your benchmarks IUU ring was slower than EPOL? It's a good question. Firstly, I like that it's mentioning your benchmarks, because I can imagine benchmarks where IUU ring probably is faster. It's just in mine, it was not faster. And my current theory is that IUU ring, while it allows you to remove system calls, it requires more work done on the kernel side for every operation that you submit. Again, it's my theory. It's I think what is happening. I have no confirmation, but it's a plausible theory. The thing is with EPOL, CACU, IUCP, and other similar things older than IUU ring is that you register sockets explicitly in those backends, and they will track events happening on that socket until you unregister them or close those sockets, right? So what happens at the registration, I imagine, is that the kernel will attach some sort of tracking to those sockets and to quickly deliver events to your EPOL whatever. And this action of registering socket probably is expensive. You have to find the socket, you have to attach to it until event happens, and then events start happening and you deliver them to user space. In IUU ring, there is no registration. You just can submit any operation on any file descriptor. There is no registration step. And what happens, I think, is that when you, for example, want to read the socket, you submit it to the kernel has to register the fact that you want to read this socket in the socket object, and when the reading is possible, it's done, and then this tracking should be removed from the socket. So it has no after effects after a ring operation is completed. And I think this, like I said, this action of registering events and unregistering them in a socket is very expensive, probably. And I think this is why IUU ring is slower.
Yes, we have another question. I can read it. This one, so this is the question from Leandro. Does the scheduler work with other kinds of sockets than TCP? Maybe UDP or Unix domain sockets? If yes, did you benchmark them?
With UDP, it should be working. I did not benchmark because I did not implement an easily usable UDP socket yet. Like with TCP socket, it's pretty much out of the box usable. UDP I did not implement yet. Unix domain sockets I did not bench either, but there is not much sense in that. To be honest, they are not very usable in production because it's local sockets. They are very much usable in tests, very handy, but otherwise in production you usually have real networking. In UDP, I can say that I don't have benchmarks available in this open source version, but in closed source version, and part of it is not out yet. We did have UDP socket, which was very fast. It was like millions of tasks as well, but I did not compare it with Boost. So it's pointless to mention any numbers unless I implement benchmark where I can compare it with something. Then I can give more results, show more results. I think this is all. I don't see any new questions.
Yes, thanks a lot, Vlad, for the insightful talk. I think all the audience enjoyed it. Anyway, guys, you still have an opportunity to leave your comments, also your insights in the comment section. It shouldn't be only questions, but you also give some feedback, insights, discuss something with each other. So at the moment, So thanks again, Vlad. It was nice having you. And we are almost wrapping up. I would just like to give a really short word about tech internals again, about the conference. So now you can evaluate the level of the talks that are given by our speakers. So both Edoardo and Vlad, they're representing tech internals, and we are really proud to have speakers like them. But please remember that this is like kind of a demo version of the big conference we're having in May in Berlin on 26th of May. So in order to learn more about the conference, you should follow this QR code. And also, this is the special discount for the ones who joined us today. So it's TIC promo 10. Please use this promo code in order to get the 10% discount. In here, you can, again, I will maybe give you another 10 seconds to write it down. And we also will share it with you via email. So you can, again, look at it. Then, of course, in here you can see the amazing lineup that is fully completed at the moment with architecture, development, system design, and high-load associated topics. And we also got speakers from Netflix, Red Hat, Dropbox, Uber, Cloudflare. So lots of companies that are joining us, and the level of talks is extremely high. Guys, we had like around 5 speakers from one spot, and we were forced to choose between those amazing talks. So you can check against the lineup. And lately, of course, if you would like to expand your ticket, again, this is just for the people who are who have joined us today. You can scan these QR codes. I know there are lots of QRs, but I know that you guys have your phones on your hands for sure. So please scan them. Book a call with me. I will tell you more about how to how to expand your discount, and also how to become a part of a TIC community. You can become a speaker, you can become a part of a program committee, you can become a volunteer. So basically, please join us. Yes, this is the aim of us, to build a community for the developers to exchange their knowledge. So a couple more seconds for you to scan. Anyway, if you would like to receive a Calendly link or lineup link, you can just leave your comments on meetup.com as well. And we will provide you this information. And final point is that this is not actually our last meetup. We are having another one on 6th of March, really close to the International Women's Day, but basically this is for everyone who would like to join us. It's going to be offline in Berlin. You can check against the topic. It's going to be like extremely insightful. We've got 2 amazing ladies representing us. So it's Veronica, the DevRel specialist, and also Maria from Zalando. I'm pretty sure that you are well aware of Zalando. So yes, we will have this meetup. We will have some prosecco. We will chat. We will give insightful talks as usually. So yes, I think this is all from my side. And now I would like to say again thank you for all the attendees that joined us today, to our amazing speakers, and see you on our next meetup. Thank you. Bye.